Oh, thank you, Papa.
Okay, hello guys.
Hi,
Can you see the desk? Is it okay?
Yep.
Okay, good. Okay, so today is our numbers and names number 14. And the theme today is language of math. So math as a language and some consequences of this. So what we will have out of this. First of all, how was the previous questions? Are they okay with you?
We didn't try them, unfortunately, because we've been trying to figure out symmetries and how the functions work.
But did you try or don't? I didn't get it.
Yeah.
Not from the last lecture.
Oh, so you didn't. Oh, that's a little sad.
I have to spend a lot of time bringing the kids up to speed. They can't keep up.
Mm-hmm. Okay. So it's a little sad because I hope that you did that. Okay. So can you do it? Can you do it? You need my help with this.
We spent about 3 hours on the questions, but it's just there's a lot that we skip over.
Mm-hmm.
We're just moving a little bit too fast for the children. That's all. Like I said, they need a lot more time on simpler concepts like the functions, the symmetries. Basically, we spent maybe 2 or 3 hours discussing symmetries on the y-axis and on the x-axis. That's a few lectures back.
Yeah, that's okay.
Yeah, that's okay.
But you have to definitely. My lecture is just just the general things, and you have to walk around, to find out your ways and everything like this. We cannot go without it. So that's normal. Work hours, yeah, it takes hours, of course. Okay, so I still hope. I don't want to repeat these things or to solve these problems for you. So just tell me, can you solve them or you cannot?
We haven't even looked at them because we were looking. We just talked a little bit about symmetries, and when I realized that they don't understand how the symmetries work, symmetries around the axis, symmetries around the origin, I had to go back and start talking about basic things like x equals y, x equals minus y, f of x equals f of minus x. That.
Okay.
Fortunately, the answer is we didn't even look at them. I prepared them, and when I started talking about them, I realized that they're too far behind, and so the answer is no. I'm not.
Okay then. Okay, so what I think that we need some more examples on what symmetries are actually, and it would help a little. Okay, so we talk about still this thing, language of math, and we'll return to the questions if you have some problems with them. We'll return to them and we'll have another maybe lecture on this particular mathematical symmetries. But we'll talk about it anyway in the future. So we just right now we just getting some general positions and trying to open fantasy to understand the things. Okay, so language of math. I hope you understand already that mathematics is actually a language that is describing things which are not mostly not familiar in our common life, except maybe when you go into the shop and counting your money right in your pocket. But all the rest things belongs like maybe to physics or some special, chemistry, some science there and there. So it looks like that mathematics is a little off the real life, but it's not true. And especially about modern mathematics. Modern mathematics is much closer to common life, much closer than people usually think. Because modern mathematics is not only about numbers, mostly about some other things, like about these operators, symmetries, and even more. The categories of language and lots of other things. So, and then we particularly touching these parts of modern math step by step, just for you to understand at least the parts of the picture. So anyway, you definitely understand that there's a lot of interesting things lay in this vector formula. Remember this triangle, right? this summarizing of operators, and in particular, this operator can be called I, this J, and this like K, right? And we have this thing that when one operator goes after another, so J goes after I, we have vector K, right? You see here. So this is the sign that there are vectors, or operators that are oriented from point to another point, from this point to this point, and this point to that point. 3 vectors, right? So one I, and usually they say it's a group operation, so often they say multiplications. So they say I by J equals K. That's how it is said. I by J equals K. Now let's try, first of all, try to make some other multiplications or group operations for this triangle. I and J equals K. Now let's try J to K.
I.
No, J, not I.
What
J.
equals I?
J.
J equals I, like how you said.
No, just J. We want to J by K. But you see, they are not going like one from another. This vector should start from here, right? But it starts here, right? To have a triangle, J by K, right? We should have K with opposite direction. That's understood or not?
Yeah.
So we have to use not K but minus K. So we just opposite to K.
Oh
Yeah? So if we put it here, so here it's minus J to minus K. And if we see this triangle, right?
yeah. Yeah.
This triangle, what the result be? We have I here, right? It looks like it's in triangle. But if you see when vectors goes like this, J and then minus K is here, right? From here to here, opposite to K. So what we have here then? The result of this, J to minus K. What do
You
you
have
think?
you have I.
Eh?
Yeah.
I?
Yeah.
This triangle, this and this. Okay, it's like this.
Minus
J and minus K
I.
will be vector this, right? The triangle goes like this, and this is minus I. You're right. You see? So J by minus K, it is minus I. Or another way, if we use minus and minus, is J by K equals I, right? You see that, right?
Yeah.
Now let's try another thing. Let's try K by I.
J.
K by I.
J.
But if we want K by I, and we have again, we have K.
Minus I.
We should use minus K, right? First, minus K
Minus I.
and I.
Wait, it would be minus I.
Minus I times K equals J.
You see, minus K. We should use minus K because it should go like this, and this goes like this. We take opposite and multiply it by I, right? I goes in the right direction, right? So minus Ki, and the result will be
Minus J.
Oh yeah, that would.
Minus J. But what
I don't understand this.
but are you doing just vector addition?
no, it's not addition. It's group operations actually, but it looks like a vector. Yes, looks like a vector addition. Yes.
Okay, yeah. So
If we use this vector and this vector, like the sum of this or whatever, this result of this group operation will be vector this orientation, right? Remember
Yeah.
triangle, minus K to I. You understand now, Vita? We go this and this triangle. The result is that, but this is opposite to J. So this vector is
Oh,
minus J.
minus J, exactly.
now I understand
But-
why the K.
But what Katie suggested originally, she suggested minus I times K.
But just I suggest you write somewhere these things, or Antosha, you know how to do it, right? So just write for them these things and look at this, all this minus and everything. But the result is k by I equals j, right? Because minus here, minus here. So we have the result for this, three things: I, j, k, right? J by k, I, and k by I, j. It's pretty interesting stuff. This is called algebra quaternions. This is multiplication table for quaternion units. They call I, j, and k quaternion units. So this is multiplication table. And also interesting thing, if we try to do this, a, j, k. Oh, sorry, I, j, k. I by j is what? We know, right?
K.
K. So k by k, right?
It's weird.
Mm-hmm.
Wait, Paul, won't that be carry k squared?
Yeah, but what is it with quaternions? I don't know.
What can this be? What do you think?
-1?
Oh, just try. Try this. You have this vector, right? You have this vector I by j. I by j. You see here. It is k, right?
So will it be 0?
Alright?
0?
That's what I was thinking.
If you think.
Okay, let's try this. I by j by minus k.
K times minus
Yeah.
k would be minus k though.
Okay, and let's try to put this vector. This I, this triangle, this is j, right? It's okay. And minus k goes like this, right?
Yeah.
So if you have this triangle, this will be what? This easier to understand. This triangle. It goes to the same point when we started, right?
0.
0, yeah, but we have sort of multiplication here, right? So something that does not change the result, right?
Origin? I mean, or not origin, identity.
Yeah. Some operator that does not change anything, because we come to the same point where we started.
Identity.
Identity, yes. And what is identity in this case? What we can use as identity here?
1.
Do you understand, guys?
No.
No, because mine is 1 times
What's
1
identity?
is still minus
What's
1.
identity?
This is an operator which does not change anything.
What?
Identity operator, remember? I denoted it like E before. It's a thing that when multiplied by any other operator, R by E is A. A by E is A. So it does not change. It does not change a thing. Like,
1 in multiplication is identity. 0 in addition is identity.
yeah.
It doesn't change.
Yeah.
So pretty often it is called like 1. 1 equals A. So this identity operator, 1 or E or whatever you call.
Okay.
So these three vectors together, they give the identity. So ij to minus k will be what? 1.
1.
Because it returns us to the same point where we started, right? To the same point. So this is identity operator. And then from here we have I, j to k will be minus goes here.
Minus 1.
Minus 1. Exactly. And because I, j is k, right? We have k by k
equals minus 1.
equals minus 1. The same thing goes by a, so it's k squared. It's k squared. The same thing with I squared and j squared. They're all minus 1.
Huh. It's pretty cool.
Yeah, pretty cool, yeah. So this is called algebra of quaternions, right? So think of this and talk to your papa on this, because it's very important thing. And because of this triangle of operators, and the thing that all these things are actually universals. Remember this universalia, right?
Yeah.
It can be applied to almost anything in this world. So it's a very important thing. But usually these three vectors they are displayed like this, not like this, but usually they're displayed like this, like I, J, and K. And
Oh, that's what symmetry.
does it resemble to you something?
Yep.
What does it resemble?
Symmetry.
Well, no, but Katya, what does it resemble to?
3D.
What's it called? The y-axis in the x-axis.
Exactly.
The y-axis. It looks to me. You know the y-axis and the x-axis.
Mm-hmm. Exactly.
Yeah.
Exactly. Yes. Exactly. And if you look at this, multiplication table, it's easier to remember like this. This is just for memorizing. It's not the real picture, but just to memorizing. Like J and K, and like this. So what is this? This is just for the memory. A by G is K. J by K is I. Again, I by G is K. And you go opposite. I to K is minus J if you go opposite to this direction. This is clockwise, this is counterclockwise. K by J, again, minus I. So this is a very, very cool thing to remember how to operate with these quaternions, right? But anyway, what you saw here, right? If you multiply, like for example, I by minus I, right? You'll get 1, right? Remember, I squared is minus 1, so I by minus 1, but minus I will be a 1, right? So we have to add another axis, and that will be axis of normal numbers, 1. So actually the algebra of quaternions, it contains four coordinate axes, and because of this, it describe the space-time. So 3 space coordinates and 1 time coordinate. So this is very important thing. Just think about it. Okay. Now about language of math. Remember, we're talking about axioms and everything, right? And the laws of this and that, morality, beauty, and inventions too, and logic, and all that sort of things. And when we talk about axioms, we saw that nature actually nature works with not only our axioms that we use, but the opposites to axioms, which looks like we're not using them, right? But they're very significant, because nature works with all of this. Just for our survival, we need particular.
Can you take the opposite of an axiom to create any new thing? For example, the opposite of geometry axioms to create a new one.
Yes, I told you, like there was a guy in the beginning of 20th century, David Hilbert. He did exactly that. He put the opposites to the axioms one after another, created lots of different geometries. So they are maybe useful somewhere in the future. For now, maybe not. One axiom of the parallels, it's very useful. It is used very widely in science, and it goes to non-Euclidean geometries. Remember these curved spaces and everything like this. So what I'm coming to. We need some mathematics that actually takes into account not the axioms that we used before, right? But some other axioms which are oppositions to these axioms. One by one, and we have not only we have not only like geometry axioms, so maybe axioms of arithmetics or algebra or whatever, but also physical laws and all that kind of things.
Is
Yes.
this sort of like negating?
Yeah, negating. Negating each axiom.
Yeah.
Step by step, one, another, then another, another, and look what is going on. And then we can come to some picture which describe our universe more in more details than we had it before. And that's how the idea of some universal math came into to this picture.
Oh,
What actually happened? What actually happened? You know that math is a language, right? So can we create some language of math that actually do not have axioms at all?
no, we can't.
Just think about it. Can?
Yeah,
Okay.
Because without no axioms, there is no math.
Yeah.
But if we have one axiom, right, and then negation of this axiom, right? So this is the whole world, right? The whole world, like whatever are they, this half, this works here, this half works here. So we take this and that, we describe the whole world. Or no?
Yeah, then you can.
Yeah. So we just, exactly, when we go with axioms and then negations, and then another axiom and its negation, and go like this, right? We can go to describe the whole thing. And that's how it may be thought about it, right? So that's how we can start about it. One thing. Then another thing. Remember we were talking about this universalia, right? Which are useful everywhere, and universalia, this opposition is this universal thing, one opposition thing. Then these triangles that we talk about, again, this is universal to everywhere, and some other things, right? So the same thing goes to the, if you remember, we were talking about music and poetry, so they're used there. Then inventions, again this triangle, right? And oppositions and all that. All these things are not only universal, but they are closely connected to the beautiness of this world, symmetry of this world,
Yeah.
mathematics and everything. So, and that kind of thoughts actually led to creation of a language, and in 1990 a Russian scientist Valentin Kulikov,
That's you did that.
this scientist reported in Kaluga about that kind of language created actually.
You?
To that moment, the language included about 3,000 to 5,000 words of this language, and it was tested on children of different ages and the grown-ups.
You know
So
what
yeah, that was, but that was not only me. That was the whole group working on it. I was the lead of this group, and the language, in short, goes like that. Remember,
That's
there.
amazing.
Huh?
That's amazing.
Okay. So, so the language was created like this. So, let's talk about how people communicate. Like, if you have language, you have communications, right? So one person, like, talks to another person,
Yeah.
right? Okay, and says something like table, right?
People.
Table.
That's
When you say table, when anybody say any word, right? There's some. What is the word? Actually, there's some sound, right? Some sound of phonemes. It's called the pieces of. So we say table. You have something in mind.
not exactly to us.
You have something in mind. So, for example, when one guy talked to a lady, right, about something about the table, he has something like maybe like this, you know, like table in the bar, for example. It can happen, right?
Yeah.
So he has a certain table on his. But when she listened and hear this word table, what got to her mind? Nobody knows actually what is her mind. Maybe it's something like kitchen table.
When I think of
That's what I think.
when I think of table, I don't think of anything. I don't really know what to think. I just think about how weird that guy is.
Okay, maybe somebody may think about just a word table, not even having anything in
I'll
the
think
way.
about
I don't know.
Just table as a word. I say table is okay, table. Table, that's okay, no problem. But anyway, the other person have something else, right? So how they communicate actually? That's a big question actually. How they communicate? She answers something, right? Table, maybe chair, right?
Yes.
Again, she thinks about that chair like this, maybe like a kitchen chair, right? And he's about these high chairs, you know, this that are useful, like maybe in the bars or somewhere. Again, different chairs, or maybe something totally different. So how they can communicate? There's a big question. If you
Well,
think,
maybe.
Mhm.
Well, maybe because like there's a certain the main idea. Like you get the main idea of it.
main idea, yeah.
We have a consciousness.
Yeah, consciousness, that's too serious thing to go into. We may talk about it a little later. But first of all, yes, this is the main idea of table. So is this has something to do with this? Main is a very general thing, right? Something. But if we talk about main idea, right, of anything, we should understand, remember this one thing, that if you're talking about language, right, so anything can be represented by what?
Words.
Words or
Symbols.
symbols, and symbol can represent
I know it's not.
anything. Anything. And symbol is whatever you say. It may be a word, maybe a sound, maybe some object, right? Chair. Can chair be a symbol?
Yeah.
Why not? You say,
Sweet symbol.
look at this.
For some people.
I got a chair, I got a chair and say, okay, let's think that this is the starship.
Marijuana can be the healthy eating for drunk people.
Can I do it?
Yeah.
Yeah, I can. Why not? So symbols or any other objects, they can play as an actors on this theater, right? Okay, let it be the starship, and I'll be an astronaut. I'll sit on this chair, and okay, we go, right? So is it why we can understand each other still? Why one say table and another have something like table but not exactly?
Because we were taught by our parents, or we got this thing.
Yeah, some universal education, right? So because everybody has these tables around, right? And we sit at these tables on the chairs and blah 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 blah, all that sort of
If
thing.
I would take everyone in mind, it wouldn't really matter, just so long as
Yeah.
you get the main idea of it.
Table, orange, lunch, drunkenness, cantaloupe, Sasha. That's the main idea.
And again, remember that all these tables, right? They have chairs around, they have people around, people sit around, and all these relations, they have connections between each other. This chair is connected somehow to that table. This chair is connected somehow to that table. People are connected to all these somehow to the table. They can sit on the chair and sit at the table, right? So there are relations between certain things in everybody's mind. And if we have this thing, if you have that kind of modeling reality, the things are playing certain things in this head or that head, we have the situation exactly, again, this nice word, isomorphism. Isomorphism. Objects. This object relates to that object. This table and that table, right? This chair relates to that chair. And relations between this chair and this table and this chair, those relations are, again, connected. this relation plays the role of that relation. And it's called this isomorphism. So the model works. Each person inside their brains, they have a model of something, of his own world. Another person has another model of his own world, but the worlds are isomorphic. So they are somehow connected, how they play with each other. So the world in this brain is like a theater where actors play like here in his brain, and back and reverse. And we have lots and lots of models in our brains, and we use words as a symbols, which have meanings for one person, one meaning, for another person, another meaning, but we have the same word, like table, right? The same word, and it is used to represent this and that and that and that. Lots of different situations. So this is the whole mystery, the whole trick of language. This is universal symbolism, universal isomorphism between the modeling, between these theaters in each other's heads. I don't know. Did you get the idea?
Yeah.
Okay.
Yeah. Good job.
Uh-huh. Yes. Listening.
Never mind. It's slipped out of my head.
Say it again.
It slipped out of my head.
I'm not getting this. Okay.
No, Visa forgot what I was gonna say.
Okay. Okay, no problem. So, just a little understanding of this. So, now we see how this isomorphism or universality really works in language. Okay. Because everything is, any symbol is universal. Like we have the sound. Like we can use sounds as a universal symbols for anything. That's what we do in our language, in our speech, right? So in our speech or language, in written language you have letters, in speech we have sounds, right? So each sound sounds like I would say a little closer to Russian because it's the alphabet is much more suitable than the Russian alphabet. So we have some sound of right?
Yeah.
And when we say what it means that we not saying anything, right? Then there goes the sound, which is oscillations of the air, and then we finish.
Yeah.
And this is what we call right? This nothing, nothing. So we have at least two stages. First stage is the beginning of the sound, or the birth of the sound. Remember? It goes birth, and then the
Birth, Visa.
going.
Crucifixion.
That's removing of the sound, the death of the sound, right?
Yeah.
And the sound itself is
The middle
life of the sound, right? So the sound itself, life. And again, what we have here, we have apparatus, birth, death.
It's a fixer.
Yeah, exactly. So in this language, which is started, we have what, the beginning of A, the end of A, and we have life of A, or the whole of this, whatever. And just the sound, just sound Now we have what else we have in language? We have intonations. Intonations.
Gestures. Did we have gestures?
Oh yeah, you can use gestures with this. Yeah, easy with these things. Yeah, of course. You can use it as gesture like gesture, no gesture, right?
Yeah.
So it's the same thing. Same thing. You can use any symbols here. So it's universal, but in many cases, because we are speaking in language, like speaking as a speech, right? So we use sounds, right? So each sound has beginning and the end and life, right? Then we have the pause between them, right? Between there's other sound, right? Then we have tones. Tones is a pitch, right? Remember this pitch? Or frequency. The high frequency, the high pitch, the tone, right? We have different tones. So we have not only this, but we have intonations, right? So we can say we can say right? We can say There are three different tones. And actually in our speech we use these intonations. The nation goes like this, up and down, like questioning something. Like we say what, it goes up. When we say what, intonations tone goes up. And we have what, we have this goes down. Statement, the answer. This goes down. What goes up. So intonation is used very, very often in a very serious way in language. So it is a part of this universal language that we're talking about. In this report, by the way, the language was reported as universal interstellar language because it is based on math. It is based on math symmetries. So like we have symmetry here, birth, death, life. If we have pitch, some tones, right? So the high tone, the low tone, again up, then down, and we have again this triangle, right? So low tone, or it is in music it is called tonic, the bass tone. Then it goes here, and then go back to tonic or something close to tonic. It depends. Again three things. Okay, so these things like the sounds, the pauses, and the pitch and tones, they form what we have, what is called rhythm of language, and actually rhyme too. Rhyme, I forgot how to spell. I think it's like this, right?
Rhythm.
Rhythm, rhyme.
R-H-T-T. Wait.
Rhyme. This rhythm.
R-Y-M-E.
Okay, you can spell it correctly. You can take a look how to spell it correctly. But this is rhythm is just goes up and down the stressing, right? So you can say like a table stressed on this, right? On table, not table, right? Table. We pronounce table, right? Some other things, the other phonemes are stressed. So rhythm, rhyme in poetry, mostly used in poetry. And we also have intonations. We talk about it, right? Just intonation. Now, if intonation goes up and down like this, it is very close to situation in music. This is called arpeggio. I think it's Z here. Arpeggio accord or chord.
Chord.
Chord. Arpeggio chord. So toning up and down, some tones here. It's like on the notes, right? Here, right? On the note lane. And we have arpeggio chord. In phonemes, so-called phonemes like a, o, u, in Russian it's u, or u, right? And e, like this e, right? This is Russian.
Yeah.
Russian. These are again chords, but chords that are called harmonic. Harmonic means that the tones goes not one after another, not in sequence, but one at the same time. Remember, for O, it is like octave, second octave and third octave. Here differences between the tones are one octave. And or is a very harmonic sound. That's why it's closer to what is called like calm, right? Calm situation. very balanced situation. Very nice.
The harmony.
And harmony, yes. And A in anharmonic, not A, anharmonic, this is A. Anharmonic, or it is called dissonance. This is called consonance. And here is 1 and here is like 7. So 7 octaves here. It's a very big difference, and it sounds like very sharp, like you know, this is something like aggression, or maybe something like some sort of explosion. So it's a very uncalm situation. Uncalm situation. So it's very general. If you're talking about meanings that are connected to that, so it's very general meanings that O is just like stable situation of anything where we start, right? When we start, and A is something something goes unstable, something appears. So this sound like this operator OR, it may mean that something really begins, explodes, appears suddenly. So that's why it's something it may be used in speech, and very often it is used. It may be used as English hi.
Oi.
Somebody came. Hi, oi.
Like oi.
And opposite to this, no, this is pronounced oa, and this is pronounced ao.
Oh,
So this is by, right? Something like this.
oi.
It's very general, but you understand like that oa it is like I, right?
Oi.
And that's like J. Remember these quaternions, right?
Yeah.
And you have something that concludes the triangle, right? So it will be OAO, and this is K. So up and down. Remember? So what I mean here, that step by step, in this way was created the whole language with the words, syllables, everything, right? And in each stage of it, we have this universalia, we have this I, J, K quaternions, and they interact with each other, and they actually display sort of rotation. So it displays like situation like something like this. This is rotation, like up and down, not only up and down, but right and left, and all these things. But this is abstract, mathematical abstract. But in the real language, it's rotation of the certain things in the world. Like something comes, something go away, something is turned, something is transformed, but in each place is described by one and the same relations, like quaternions, I, J, and K. They may be displayed in mathematics, like usual mathematics, like I, J, and K, as I just shown to you, or they may be displayed as a language. And we are a little already out of time here, but anyway, when we go further, we comes to many things there. Like we have this A, O, and Da. They are so-called vowels, right? You know this word?
Yeah, vowels.
Vowels.
Yeah.
Vowels. And there are also consonants.
Yeah, non-vowels.
And non-vowels are something like which were very difficult to pronounce if there are no vowels. With no O's, right?
Yeah.
So this is actually interesting. It would be interesting thing because consonants, if vowels goes from the sound, consonants mostly goes from the pause, So something that actually distinguish one vowel from another vowel, something in between, and it evolves. And there are lots of consonants. They have certain meanings, and these meanings go to syllables and everything like this. And interesting enough, of course, because of this universal thing, you can use the same words the same words in very different situations, like mathematics. If you use like x variable, right, maybe any number, the same thing here, any syllable or any sound, even word or sentence, can describe very different situations. So one person can speak about his own things, and other people can think about very different stuff. And this is a very important thing, because it helps you to invent things. If you think about your own field and you express it in this language, by the way, the name of language is dial, like from dialectics. Dial.
Uh-huh.
So you can speak in one field, another guy can speak in another field, and you can speak to each other. Like mathematician can speak to physicists, physicists can speak to a medical doctor, medical doctor can speak to the artists, artists can speak to the writer, and they can speak about their own fields and still understand each other and can help each other.
Yeah.
Did I have a question?
Yes, sure.
Mutual need.
Do you have any questions?
You said about question. What question?
Do you have any questions for us?
Oh yeah, I have questions. Yes. Do you have questions? Because we're finishing.
Okay.
Okay.
Mm-hmm.
Okay. Thank you, Dada.
What?
No questions?
No, but thank you, Dada.
Okay, guys. Okay, do you have a pen? I'll give you my questions. Okay.
I'm writing down.
No, Dada.
Lisa, I have this.
Papa's writing it down.
Okay, got you writing?
Yeah, Papa's not here right now. Papa's busy. We have a bird in Dita. We have a bird in our vent. So yeah.
Really?
Yeah, that's why the air conditioning just turned on and now it's off.
Okay, guys. Okay, we'll talk about it later. Okay, because I'm recording now. So okay. So now questions. Okay. You write it, right? Write down.
Yeah.
Okay. The first question is, and think about it. How it comes that without axioms we still have certain rules, right? We have certain rules.
So without axioms, we have.
We still have certain rules. How can it go together? How comes? Just think about it and tell me later. Okay? How comes that without axioms we still have lots of rules actually? The second question is.
Oh wait a second. We have certain
Sure.
rules. Okay.
Mm-hmm. Second is, like if A, right? A
Yeah.
denotes your job office.
If a what?
Like this is a symbol of your job office, your work office.
Uh-huh.
Look, you're working somewhere, just imagine, right? Like your school, whatever.
It was where you work?
Yeah. Your office, right? So how would you think in this language, right? How would you think to express repeatable coming there, day by day? So coming today, then after today, then again and again and again. Repeatable coming. How would you express it using this one sound and what to do with it, okay?
So how would you express?
Repeatable coming to the office each day, day by day.
So how would you express going to the office each day?
Yes,
Office.
with A.
Day with a. Okay.
And also to this question, the same, express it with quaternions.
With what?
With quaternions, by using quaternions. The same question, but with quaternions, not A.
With what? With quaternions.
Mm-hmm.
Quaternions. I don't know how to spell that.
whatever. Yeah. Quaternions is Q, U, A, T, E, R, N, I,
Sweet.
O, N.
QUA.
QUA. Ternion. Quaternion.
Yeah. Okay.
The third question. Just think. How we can understand each other when each of us has something unique in his mind. We actually talked about this, but just think about it yourself, okay? Just think about some examples, whatever.
With our own ideas?
Yeah, how you exchange these ideas, okay? How you speak. Let's just think about it, okay? And give some examples. And the fourth question.
Oh, wait.
The fourth question is.
Is that the last question? The fourth one?
Yes, the fourth is the last, yes.
Alright. Sasha, after this, I'm going back to you.
We have certain things in the language which are called prepositions and pronouns.
Uh-huh.
You know what is this?
No. With what?
Preposition and pronouns. Pronouns. Prepositions are, I think you know, like to, at, in. Understand, right?
Yeah, so we have to in.
No, there's different. They're called prepositions. To, at, in.
Okay, wait. So, preposition.
Preposition, pre.
Okay.
Not pro, preposition. Like many of them. In English there are lots of prepositions.
Uh-huh.
You can to, at, in, over, whatever. Okay?
Okay.
Now, and we have pronouns. Pronouns are like this. I, right?
Uh-huh.
Me, you, it, that, and something, you know.
So, and, me, you, it, and that.
And many of them too. They're called pronouns. You understand the idea, right?
Yeah.
Me, you, it, that, right? And in this language, just a fact. In this language, they are very close connected. Actually, prepositions and pronouns are in the symmetry of oppositions. Opposition symmetry. It's just a fact. Just a fact of language. Huh?
I don't need to write that down.
Yeah, that's there in opposition symmetry, yes. Those two are opposition. They oppose each other.
Okay.
And the question is, why do you think it's so? Why they're opposed? What kind of symmetry is it? What is it? Just why is it? Just think about it. Why it comes like this?
Why do they oppose?
Yeah, why they oppose? Yeah, why this? What's inside this? Why they really oppose each other? Like me, you, and to it. You know, just think about it.
Yeah.
Okay.
Okay.
Okay, that's it. Okay, guys. Okay, guys.
Well, could you talk to Babu?
Yes. Thank you very much. I'll just.